Guys, last time we talked about undetermined coefficients, superposition approach. Today's class is about variation of parameters. Okay. So what we need to study this one says basic integration formulas and techniques from calculus, and everybody's expert here, right, about integration. And as an introduction in the previous classes, in 4.5, 4.6 is about undetermined coefficients, right? Superposition approach. The second one is annihilator approach. Okay, in this chapters 4.4 undetermined coefficients, actually we just solved differential equations, right? Linear differential equations with constant coefficients, and our g of x, the function, was of certain type. It was just either polynomial function or trigonometric function that is expressed in terms of only sine or cosine, or linear combination of sine and cosine, or exponential function, or linear combination of these three functions, or their product, something like this. But in the chapter we did not mention, how about if we have something like 1 over x or natural logarithm of x, in general any kind of function, okay, function of x. We didn't mention this, right? So in this part we are going to study this method, and this methods, to say, we examine method for determining a particular solution of a non-homogeneous linear differential equation that has in theory no such restrictions on it. So we are not going to put any restriction on the type of the function on the right hand side. That is our f function, right? That is not multiplied by any y or derivatives of y. And also this method due to the eminent astronomer and mathematician Joseph Louis Lagrange, who was born in 1736 and died 1833. He lived quite a long time. Is known as variation of parameters. Maybe some other mathematicians actually were dealing with this one. Maybe officially this guy for the first time published as a paper, I think, on variation of parameters, or he introduced this method to the math world or to the students at that time. Okay, so we start this class first by examining this first order linear differential equation. That we did this in chapter 2, right, in 2.3, I guess. So if you remember, if you're given the first order linear differential equation, that a1 of x, y prime plus a sub 0 of x, y is equal to g of x. How did we solve this? First, we had to actually bring this into the standard form, right? If I just divide both sides by a1 of x, in our theorem, we know that actually, supposing that this a1 of x is never equal to 0 in the interval of definition, okay, the solution interval. At that time, we can actually change this into this form. And if you just divide both sides by a1 of x, here I will have here just y prime, right? Here we have y prime plus here we have a sub 0 over a1. I'm not writing the x's. Y is equal to g over a1. And actually we are just relabeling this thing as p. So we have p of x, and relabeling this as f. So here we have f of x, right? And after that, if you remember, we just multiplied both sides by mu, and when we just found mu, we get this thing, right? Actually, what is our mu? That mu is equal to e to the power integral p of x dx, right? And after that, we get this solution, if you remember this. Now, if you look at this, okay, let me not write this one because I'm going to write something else here. We pay attention here. We had the sum of two things. These two functions are linearly independent. This is the first one, and this is the second one, because here we have function and multiplied by non-constant function here, right? So actually, this one is the complementary solution of this equation, and this one is the particular solution. Okay. Now, how do we get this in different way? If I know this one, if I just consider this, this is the first y sub 1, this one is y sub 2, right? Now here we have our solution is in this form, c sub 1 y1 plus c sub 2 y sub 2. Okay, but actually if you pay attention, this one is the solution of the associated homogeneous equation of this dE, right? Because if you substitute here, for example, let's say y1, if I just take this y sub 1 is equal to e to the power minus integral p dx. If I substitute into this equation, what we have here, actually also constant multiple of this one will be the solution. Here we have e to the power minus integral p dx, and here we have derivative, right? It is prime. So here we have prime plus, and here we have p of x times and y1, right? So that's equal to e to the power minus integral p dx. And if you evaluate this, if you differentiate this, it comes to the front, right? And if you differentiate this, what is it? It's equal to minus p. So that is minus p, right? Because if you integrate the function and differentiate this, we get the original function back. And times, here we have e to the power, something that is minus integral p d of x. Plus, here we have p times e to the power minus integral p of dx. And if you have negative and positive, exactly the same thing, and the sum is equal to 0. And 0 is always equal to 0 because on the right hand side we have 0, right? Homogeneous part. So that means that that is the complementary solution of this differential equation, right? Or even if you just substitute the same thing anyway. So that is the complementary solution of this one. And how about this part? Then this part is the particle solution. Okay. Now, in this part of the chapter, we are going to learn how to find this particle solution again, because this homogeneous part we have already learned when the coefficients are constant, right? Now, if I just approach in this way, look, here, let me also change marker color. All right. So I know this solution, y sub 1, all right. So, and also we know that if this is the solution of this associated homogeneous equation, we know that from the theorem, and also it is constant multiple, right? That's a C1, C sub 1 times y sub 1. That is also the solution of this homogeneous equation. Why? Because C1, because of the linearity of the differential operator, you can just take the C1 out. On the right hand side, we have 0, and we can just divide by C sub 1, right? So now we are looking for, we will look for in this, let's say this C sub 2, that is our particle solution. Let me just particle solution. Equals. And how about instead of the C1, if it is some kind of function like this, u of x times y sub 1 of x. Okay. We know that actually this constant multiple of the first solution is also the solution of this homogeneous equation. And we are assuming that we are making assumption here this particular solution cannot be in this form actually. Okay. Now just for simplicity, I'm just going to write without this x, but keep in mind that u is a function of x, y1 is a function of x. Now if I substitute here, what happens here? So if we assume so, and substitute here, we have u y sub 1 prime plus p times y, right? And on the right hand side, we have f. Okay. So if I do so, if I assume so, is it possible to find this u? Now if I differentiate this one, what we have here, u prime y1 plus u y1 prime, right? Plus, and here we have p y. And actually, what is y? What is y? Y is what particle solution actually here. This one is particle solution, right? This one is particle solution. So that is equal to this thing. It is U Y1. On the right hand side we have F. Right. Now here, what is the common factor? It is U is a common factor. So here we have U prime Y1 plus, take this U out. So here we have Y1 prime plus P Y1 is equal to F. Right. And what is this thing? It is just associated homogeneous equation of this dE, right? So that means that this thing is equal to 0, right? Because of this, if you just substitute here, as we proved here, this one is y sub 1. This one is y sub 1, right? If you substitute here, is equal to 0. So that's why this thing is equal to 0. U times 0 is equal to 0. Now what is up here? Here we have U prime Y1 is equal to F. Now from here I can find this U prime is equal to F over Y1, right? Now we know how to find U then. What is U? U is equal to integral F over Y1 dx, right? Okay. So now if I substitute here, we were looking for this y sub p, and this particle solution will be u times y1. So here we have y sub 1 times, what is u? U equals this. So that is integral f over y sub 1, and here we have dx. Okay. So we are going to make the similar assumption to solve the second order linear differential equation where the coefficients are, what is it, constant. But on the right hand side, where there is no any restriction on the type of the function f. Okay, when it is like, once again, polynomial function or linear combination of sine and cosine or exponential function or their product or linear combination of these three functions, we already did this. But now we are just generalizing this method to any function here. Like we may have tangent of x here, for example. We may have 1 over x, for example. We may have, what is it, cosecant of x. We may have natural logarithm of x. Okay. All right. Chammakara,
Yes, sir.
did you understand what we did here?
Yes, sir.
All right, good. I'm just going to generalize this. If you understand this idea, if you didn't understand any step, you may ask now. All right, because I'm not going to write one by one because it takes a lot of time. I'm just going to explain what's going on here. If you don't understand, you can just stop or raise your hand. I may give you more explanation. Now let's consider the case of linear second order differential equation. Okay, this one is linear. Once again, why it is linear? Because we do not have a product of y by any of its derivative, or we don't have y prime squared. We don't have y times y prime, something like this, right? Every y or its derivative is multiplied by some function of x. Okay, but of course here, again, we are going to talk about this kind of differential equation whose coefficients are constant. But this is the general definition, that's why we put here. Okay. And the first step, what did we do in the previous slide? We have to bring this equation into the standard form. And you know what we mean by standard form, right? And just dividing by the leading coefficient. If you divide both sides by a sub 2, I will have here a sub 1 over a sub 2, a sub 0 over a sub 2, and g over a sub 2. And by relabeling these things, let's say a sub 1 over a sub 2, let's just label this by P, capital P, and this a sub 0 over a sub 2 by capital Q, and G over a sub 2 by F. So now it becomes in standard form. When we just say standard form in differential equation, we mean that the leading coefficient here is equal to 1. Okay. So now, if we just solve this equation, if you remember how we solve this, if the coefficients are constant, we just divide this into two steps, right? In the first step, we have to solve this homogeneous part, right? Where differential equation is equal to 0. And after that, we need to find, this gives us the complementary solution. And after that, in the second step, the differential equation is equal to f of x. If we solve this, this gives us, what is it? Partial solution. Then we can get the general solution of this equation. That is complementary solution and the partial solution. And this is how we solve differential equations, right? And so far we have been learning this method. So assume that when we just solve this homogeneous part, okay, that is equal to 0. It's a second order, so we will have two linearly independent functions, right? That the first one is y sub 1 of x, the second one is y sub 2 of x. And also we know that the solution of this differential equation will be, what is this? The homogeneous part, the homogeneous equation solution will be y is equal to c sub 1 times y sub 1 plus c sub 2 times y sub 2. Okay, that is actually the solution of homogeneous or associated homogeneous equation of this differential equation. Okay, now we are making similar guess like the previous one. What did we do here? We just assume that instead of this c sub 1, how about if it is a function? We're assuming that, but this assumption works perfectly, then it gives us, or it produces the solution. So here, how we guess here, we assume that, how about this c1 is not a constant if it is a function? Can we just look for the partial solution in this form? And when we just assume so, actually it works, it gives us the correct, the right solution, right? Also here, in similar way, that is the solution of this homogeneous equation, associated homogeneous equation, right? That's when is equal to 0. So now we are assuming that, how about this constant is u sub 1 of x, the function, c sub 2 is also the function. But does it give us the partial solution of this differential equation, So when we just make this assumption, and after that, we are looking for the partial solution. That is our partial solution. That is y sub p. You're assuming that, how about if it is in this form? Okay. And after that, I will substitute into this equation. To do this into this equation, first I have to differentiate this once and replace it with, this substitute for y prime into the equation, right? And after that, differentiate one more time, double prime here. We know how to differentiation. Just it's a long, but we know what is the rule. It's very simple. Just you need to differentiate, use that rule, right? U times v prime equals u prime v plus u times v prime. And again, substitute here. What we are doing here is this. Okay, why we are assuming that this is the partial solution of this differential equation. And since, as you see here in the equation, we have y prime and y double prime, I need to evaluate these things. So y prime equals this, and I'll substitute here, and y double prime equals this, and substitute here. When I do so, substitute and reorganize this. So here we have y partial solution double prime, p times yp prime, q yp. Yp prime equals this, and yp double prime equals this. Substitute and reorganize. Okay. The idea is, we know that this y sub 1 is the solution of the associated homogeneous equation. So I'm trying to get this expression. That means that y sub 1 double prime plus p times y sub 1 prime plus q times y sub 1, that's equal to 0. But in the expression, we have this thing here. u1 is a common factor, u1 double prime plus p times y1 prime plus q times y1 prime. So that's equal to 0. And also, actually, here we have, because the linear combination of these two things, we have y sub 2 double prime plus p times y sub 2 prime plus q times y sub 2. That's also equal to 0. Okay, so these two things gone. What is that here? The remaining part is this. Okay, now again, if we just make some factorization and reorganize this, we get this form. Okay, we get this form. Because as see here in the previous one, what is this? Here we have y1 prime u1 prime plus y1 and y1 double prime. Okay, Anyway, when we just actually organize this, we will get this expression. And again here, these are just differential operators. I can just take this out. Inside, we will have y1 u1 prime plus y2 u2 prime, right? So we will have this expression. Just take this out. This thing is here, and this thing is here, right? Because we know that the differential operator is linear. And here we have the same thing here. And also here we have the same thing, okay? And on the right-hand side, what we have f of x, okay? So now, how many variables do we have? Here we have two variables, right? We are looking here for u sub 1 and u sub 2. We are looking for this. So we have two variables. To be able to solve these two variables to determine, to find their solution, to find their value, we need to have two equations, right? So I need two equations, otherwise we cannot find their value. At least two equations, actually. With three we don't need, but two variables, we have two equations, we can find their value, either by elimination method or the substitution method. So here, I'll just make a further guess. Okay, how about if this thing is equal to 0? These two things are the same, right? Y sub 1, y sub 1, u sub 1 prime, u sub 1 prime, and also this is the same. And this thing is equal to 0. Okay. So if I make this assumption, then here is equal to 0, right? And this thing should be equal to f of x. Now we have two equations, two variables. So it's a kind of, it just opens the way for us to be able to solve this equation. All right, because we are just assuming something, and now we are checking this assumption is correct or not. If it is correct, then that's what we are looking for. Okay. Now from here, I need to solve this system of linear equations. Okay. How to solve this? It is easy. You learn this in linear algebra. But here to solve this equation, we are going to use Cramer's rule. Okay. And if I just write this in matrix form, what we have here? We have the coefficients. This one is a sub 1, b sub 1, a sub 2, b sub 2, right? These are the coefficients. What is the unknown here? u1 prime and u sub 2 prime. These are the unknowns. So here we have x. So here I have something like this. However, this matrix is, let's say it is w here times, here we have vector x, and on the right hand side we have vector b. Okay, these are vectors. Why we have something like this? So now I need to solve this. To solve this one, Cramer's rule states that when we solve this, anyway, u1 prime will get this thing, and u2 prime we get to this thing. Okay. Before I continue this, let me just once again remind you about Cramer's rule. Maybe I need one slide, empty slide here. Where is it? Where are we now? Here. Okay. All right. All right. Cramer's rule, it is like this. A sub 0, let's say here we have x plus b sub 0, here we have y is equal to, not a sub 0, let's say a sub 1, b sub 1, so here we have c sub 1. So here we have a sub 2, x plus b sub 2, y is equal to c sub 2, right? And from linear algebra, if I just write this in matrix form, we have something like this. Here we have a sub 1, b sub 1, a sub 2, b sub 2, right? And here we have x and y. On the right hand side, we have c sub 1 and c sub 2. Right. Now, let me just denote this matrix by A. Okay, that is matrix A. All right. And also, I will define another matrix. Actually, this A sub 1, let's say A sub 1 is the same matrix this, but the first column is replaced by this vector. So at the time, we will have this thing, C sub 1, C sub 2. Here we have B sub 1, B sub 2. And also let me define another matrix, A sub 2, that is, this is the same matrix, but the second column is replaced by this vector. So that is A sub 1, A sub 2. Now here we have C sub 1, C sub 2. Okay. And after defining these two things, Cramer's rule states that then here the first solution, that's X, is just equal to determinant of A sub 1, determinant of this matrix, over determinant of A. And you know how to evaluate this determinant, right? And how about the second solution? Y is equal to determinant of A sub 2 over determinant of A. Okay, but here this is just example for a system of linear equations with two equations. But actually, it works for any square. How to say, any system of linear equations that has n variables and n equations. Okay, it must be square, of course, otherwise we cannot evaluate the determinants. If it is maybe 3 variables or 3 equations, 4 variables, 4 equations, the same idea. Okay, A sub 1 means we're just replacing the first column by this, A sub 2 the second column, A sub 3 the third column by this. Okay, so that is Cramer's rule. All right, so also here, all right, we have 9 minutes left. Let me finish. In the second session, we'll solve problems. So that's also maybe just different things, but it's just system of linear equations. These are the unknown. These are the coefficients. Maybe these are not the numbers, but functions, but these are the unknowns, right? On the right-hand side, we have 0 f of x. Here we have 0 f of x. So this one, if I denote this with w, then w1 is the same matrix with this, but the first column is replaced by this vector. Okay, or this column. And this W2 means the same matrix, only the second column is replaced by this. At the time, this U1 prime will be W1 over W, and that is equal to, what is W1? We now have to evaluate this and evaluate here. And W2 also from here, because this one is 0, right? From here, W1 is cross multiply A times D minus B times C, that is 0 minus y2 times f of x. That's why here we have minus y2 times f of x. How about this w2? W2 is, and this is equal to 0, right? This one is y sub 1 times f, y sub 1 times f, and this one is w. Okay. And also this w, if you remember, what is w? W is Wronskian determinant. That's why we are using w for this. It's exactly the same thing, right? Y sub 1, y sub 2, y sub 1 prime, y sub 2 prime. Now, if we have third order linear differential equation with constant coefficients, at that time we will have 3 by 3 matrix here. Y sub 1, y sub 2, y sub 3, y sub 1 prime, y sub 2 prime, y sub 3 prime, and here we have y sub 1 double prime, y sub 2 double prime, y sub 3 double prime. And here we have 3 functions. Okay. And see, at the beginning we say that in theory it works, but the problem is it's not always easy to evaluate this thing. For example, if it is 5 by 5, it is not so easy. It is possible, but very complicated, very long. But it is possible. Theoretically, it is possible. Guys, I mean, a lot. I think if you have any questions about this, or if you did not understand a step, please you may ask. Let me give you 2 minutes. If you have no question, then we'll continue. Any question? Okay then.